Welcome back, everybody, for another deep dive. This time, we're going to try to understand this proposed new material called 2D-CRO. It's a mouthful, I know, but stick with me because this stuff is seriously cool. Imagine something so thin it's just one atom thick, but with the potential to change how we think about electronics and maybe even quantum computing.
Yeah, it's true. The possibilities are very exciting. And what makes 2D-CRO so interesting is that it has this property called altermagnetism, which is still pretty new in physics.
Altermagnetism. I have to admit, when I first saw that word, I thought it was a typo. So, for those of us who haven't been reading up on quantum physics lately, can you explain what altermagnetism is?
Yeah.
And why are scientists so excited about it?
Well, think about it this way. You've probably heard of magnets, right? And you know they have a north and south pole. That's because they have what we call net magnetization. All their little magnetic moments are pointing in the same direction. And that creates the overall magnetic field.
Right, like a bunch of tiny compass needles all lining up.
Exactly. Then you have materials called antiferromagnets. In these, the magnetic moments are arranged in a pattern, a perfectly alternating pattern, so they actually cancel each other out. It's like having the same number of positive and negative charges. The overall charge is neutral.
So no net magnetization.
Right. Now, altermagnetism is kind of like a hybrid of these two.
Hmm.
It has zero net magnetization like an antiferromagnet, but it still has these strong spin-dependent phenomena, which you normally only see in materials that do have a net magnetic moment.
So it's like it's playing both sides of the magnetic field.
Yeah, you could say that. It's this unique combination that has researchers so interested because it opens up this whole new way to explore and use magnetic properties in materials.
Okay, so we've got this mind-bending concept of altermagnetism. But where does 2D-CRO fit into all of this?
2D-CRO is a proposed monolayer material. It's derived from bulk calcium-based rutheniates, and based on theoretical calculations, it's predicted to show this altermagnetic behavior.
So they haven't actually made this material yet. It's still theoretical.
That's right. But the theoretical work is incredibly strong. Researchers have used what's called density functional theory, or DFT, to model the properties of 2D-CRO based on its predicted atomic structure.
DFT, that's like a virtual laboratory, right?
Yeah,
Where scientists can run simulations and predict how materials are going to behave.
precisely. And the DFT calculations for 2D-CRO are really exciting. They're not only predicting this unique altermagnetic behavior, but they're also saying that it could have some pretty wild properties.
Like what?
Well, for starters, it might exhibit what's called the quantum anomalous Hall effect.
Right.
And let me tell you, that's where things get really interesting.
Okay, I'm all ears. What is the quantum anomalous Hall effect, and why should we care?
Imagine an electrical conductor that has zero resistance. That means electrons can flow through it without losing any energy at all.
Wait, electricity without any resistance. Isn't that kind of a big deal?
It's a huge deal. It means we could potentially create electronic devices
Right.
that are super efficient. They make almost no heat and need way less power to run.
So we're talking about a revolution in electronics.
Potentially, yes. And that's just one of the potential applications for 2D-CRO. It could also be used in quantum computing spintronics, even new types of sensors.
Okay, I'm starting to see why this is such a hot topic. But let's back up a bit. If this material hasn't even been made yet, how do we even know if it's possible to make it?
The researchers working on this have proposed two main methods for synthesizing 2D-CRO. Both of them use techniques that have already been used to make other 2D materials.
So they're adapting existing methods
Mm-hmm.
to try and create this brand new material.
Exactly. The first method involves starting with a bulk crystal of the parent material, calcium ruthenate, and then carefully exfoliating it.
Exfoliating, like a facial for a material.
Kind of, but instead of removing dead skin cells, we're talking about peeling off layers of atoms until you get down to a single sheet of 2D-CRO.
And how do they do that? Do they use tiny tweezers?
Not quite. There are a couple of ways to do it. One way is to use a soft chemical approach to gently separate the layers. The other uses ultrasonic waves to kind of shake the layers apart.
So they're either gently peeling or vigorously shaking. Sounds like quite a process.
It is, and it needs a lot of precision and control. But the other proposed method is even more complex. It involves assembling the 2D-CRO monolayer, piece by piece, from a solution onto what's called a substrate.
So it's like building a microscopic jigsaw puzzle.
In a way, yes. There are a couple of techniques for this, too. One is called Langmuir-Blodgett assembly, where you carefully arrange the molecules on a surface, kind of like laying tiles.
I can only imagine the patience that would take.
For sure. And the other technique is called electrostatic self-assembly, where you use the attraction between opposite charges to guide how the molecules assemble.
So they're either meticulously placing the molecules or letting electrostatic forces do the work for them.
Exactly. And no matter what method they use, the last step involves annealing, heating the material to make sure the crystal structure is perfectly ordered.
So it's like baking a cake. You need that final step in the oven to make sure it all comes together perfectly.
That's a great analogy. But in this case, we're talking about creating a material that could completely change technology as we know it.
Okay, so we've talked about what 2D CRO is, why it's so exciting, and how scientists are hoping to make it. But let's dive a little deeper into the theoretical predictions. What makes this material tick at the atomic level?
To understand that, we have to look at its predicted structure. Imagine two outer layers of calcium and oxygen atoms, sandwiching a central layer of ruthenium and oxygen atoms.
A microscopic layer cake.
I like that. And the way these atoms are arranged, especially the way those oxygen octahedrons are tilted around the ruthenium atoms, it plays a huge role in how the material behaves. It's this specific arrangement that leads to those unique properties, including altermagnetism.
It's amazing to think that these tiny tilts, these subtle shifts in the arrangement of atoms, can have such a big impact on a material's properties.
It is. It really shows how powerful theoretical physics and computational modeling can be. We can now predict and understand these phenomena in such incredible detail.
So we've got this intricate atomic structure, but how does it connect back to the altermagnetism we were talking about earlier?
To answer that, we need to talk about electronic correlation, which basically describes how strongly the electrons in a material interact with each other. In the case of 2D CRO, there's this critical value called the Hubbard U value. It acts like a switch.
A switch for its magnetic personality.
Exactly. Below this critical value, the material acts like a ferromagnet, meaning all the magnetic moments align, creating a net magnetization. But above this value, it flips and becomes an antiferromagnet, where the magnetic moments cancel each other out. And here's the key. 2D CRO seems to be right at this critical point.
So it's teetering on the edge between these two magnetic states.
Precisely. And it's this delicate balance that creates altermagnetism, where you have zero net magnetization, but you still see those strong spin-dependent effects. And if we want to visualize this, we can look at something called the band structure, which is basically a map of the energy levels that are available to the electrons in the material.
Okay, so imagine a map, but instead of showing roads and cities, it shows the energy levels of electrons.
Exactly. And in a typical antiferromagnet, you'd expect to see a symmetrical band structure because of this fundamental principle in physics called the Kramer's spin degeneracy theorem. But with 2D CRO, there's a clear asymmetry, especially along certain paths in what's called the Brillouin zone, which is just a fancy way of describing the space where we map those energy levels.
So the asymmetry in the energy landscape is a fingerprint of altermagnetism.
Precisely. And it's further supported by looking at what's called the projected density of states, which gives us even more insight into the electronic structure and confirms this unique behavior.
This is all incredibly fascinating, but I have to admit, we're getting into some pretty complex physics here. Is there a way to make this a little more tangible, a little easier to understand for those of us who aren't theoretical physicists?
You're right, it can get pretty abstract. But imagine you're looking at a perfectly symmetrical image in a mirror. That's like a typical antiferromagnet. But then someone comes along and slightly distorts the mirror, creating a slightly asymmetrical reflection. That's kind of what's happening in 2D CRO. The asymmetry in this case is created by the tilting of those oxygen atoms, and it's what leads to those unique altermagnetic properties.
Okay, I can picture that. It's like the broken symmetry opens up all these new possibilities.
Exactly. And that's what makes 2D CRO so exciting. It's challenging how we think about magnetism and opening up new avenues for exploration.
This has been a really great deep dive so far. We've learned about altermagnetism, the predicted structure and properties of 2D CRO, and how it could change technology. But before we wrap up this part of our journey, I want to talk about another important aspect of 2D CRO, spin-orbit coupling. Can you tell us what that is and why does it matter here?
Think of an electron spinning like a top. Now imagine that spinning motion interacting with the electron's movement within the material. That's spin-orbit coupling in a nutshell. It's like adding another layer of complexity to the already intricate dance of electrons.
So it's not just about the electrons themselves, but also how their spin affects their movement within the material.
Exactly. And in 2D CRO, this spin-orbit coupling has some pretty interesting consequences. For one, it makes the magnetic moments prefer to align along the z-axis, perpendicular to the material's plane.
So instead of lying flat, the magnetic moments want to stand up.
Precisely. And this is a direct result of the reduced dimensionality of the 2D CRO monolayer. It's different from the bulk material, where the moments prefer to lie in plane.
Okay, that's fascinating. But why does this out-of-plane alignment matter? What does it tell us about 2D CRO?
Well, it actually opens the door to even more interesting phenomena, like something called Berry curvature. And that's where things are about to get even more mind-bending. But we'll save that for the next part of our deep dive.
You've definitely left us hanging on a cliffhanger. I can't wait to hear more about this Berry curvature and what it means for 2D CRO.
It's a wild ride, that's for sure. Stay tuned. Picking up where we left off, let's talk about Berry curvature. I know it sounds like something out of a sci-fi movie, but it's a real thing in physics.
Well, you've definitely got me curious. Is there a way to explain Berry curvature without getting too lost in the quantum mechanics of it all?
I think so. Imagine walking on a curved surface, like the surface of a sphere. As you walk, your direction changes, right? You're constantly adjusting your path to stay on that curved surface.
Yeah, I get that.
Well, Berry curvature is kind of like that, but for electrons in a material. It describes how the quantum mechanical properties of electrons change as they move through a material with the specific electronic band structure.
So instead of a physical surface,
Yeah.
it's more like a curved energy landscape that the electrons are moving through.
Exactly. And this curvature can really affect how the electrons behave, especially materials like 2D CRO, where we have this strong spin-orbit coupling.
So how does Berry curvature tie into this quantum anomalous Hall effect? You said things were going to get even more mind-bending.
They are. Remember how I said that 2D CRO could act like a churn insulator under the right conditions?
Yeah. And you also mentioned that this is a type of topological state.
Right. Well, in these churn insulator states, the Berry curvature creates these special channels along the edges of the material where electrons can flow without any resistance.
So it's like the Berry curvature is carving out these electron highways along the edges.
That's a great way to think about it. And because these edge states are what we call topologically protected, meaning they're really robust against any imperfections in the material, the conduction stays lossless, even if there are impurities or defects.
That's pretty amazing. So we're basically talking about creating a material where electricity can flow freely without losing any energy.
Exactly. And that's why the quantum anomalous Hall effect is so exciting. It has the potential to totally change electronics as we know it.
Okay. I think I'm starting to understand Berry curvature a little better and how it plays a role in the quantum anomalous Hall effect. But all of this is so complex. How did researchers even figure out these intricate properties of 2D CRO in the first place?
That's a great question. A lot of it comes down to the power of theoretical physics and computational modeling. Remember DFT, density functional theory? We talked about it earlier.
Yeah, the virtual lab where scientists can simulate materials at the atomic level.
Right. Well, DFT has been super important in predicting and understanding the properties of 2D CRO. By using the material's predicted atomic structure, researchers can calculate things like its electronic band structure, Berry curvature, and even how it responds to external fields.
So they're basically running virtual experiments to test these theories.
Exactly. And DFT is amazingly accurate. The predictions from DFT have been confirmed over and over again by experiments. So even though 2D CRO hasn't been physically made yet, we can be pretty confident in the theoretical predictions about its properties.
It's incredible to think that we can explore and understand materials at such a fundamental level, even before we can actually make them in a lab.
It really speaks to human ingenuity and our ability to probe these mysteries of the universe.
Okay, so we've gone deep into theory, but let's come back to reality for a bit. You said earlier that researchers have proposed two main methods for making 2D CRO. Can you go over those methods again and maybe talk about the challenges involved?
Sure. As we talked about before, the first method starts with a bulk crystal of calcium ruthenate and then carefully exfoliating it to get a single layer of 2D CRO. This technique has worked well with other 2D materials like graphene.
Right, it's kind of like peeling away layers of an onion, but on an atomic scale.
Exactly. But the challenge here is the precision you need. We're talking about manipulating things at the atomic level, which is incredibly delicate and requires specialized equipment and techniques.
Imagine it's like trying to do surgery with tweezers under a microscope.
That's a good analogy. It takes a steady hand, a lot of patience, and expertise. The second method, assembling the 2D CRO monolayer piece by piece from a solution, is even more challenging.
So you mentioned techniques like Langmuir-Blodgett assembly and electrostatic self-assembly. What makes those so difficult?
Well, both methods involve controlling where each molecule goes on a surface. Imagine trying to arrange millions of tiny magnets in a specific pattern using just a pair of tweezers.
That sounds really tedious and time-consuming.
It is, and you need an incredible level of precision. Even if one molecule is slightly out of place, it can mess up the whole structure and change the properties of the material.
So making 2D-CRO is no easy feat. It sounds like it's going to take some serious scientific creativity and new technology
Here,
to make this a reality.
you're absolutely right, but the potential benefits are so big that researchers are really motivated to overcome these challenges.
And speaking of potential benefits, let's imagine for a moment what the future could look like. If scientists can actually make 2D-CRO, what are some of the ways we could use this material?
The possibilities are really vast. Just the quantum anomalous Hall effect alone opens up a whole new world for electronics. Imagine computers that use almost no energy and don't produce any heat.
That would be incredible. No more overheating laptops or phones that die after a couple of hours.
Exactly, and it goes beyond consumer electronics. We could see it used in high-performance computing data storage, even quantum computing, where the unique properties of 2D-CRO could lead to huge advancements in processing power and efficiency.
So we're potentially talking about a material that could change the entire technological landscape.
It's definitely an exciting possibility, and that's just the beginning. 2D-CRO's unique altermagnetic behavior could also be important for spintronics, a field that uses the spin of electrons to process and store information.
So it's like we're unlocking a whole new dimension of possibilities for electronic devices.
Exactly. Spintronics could lead to devices that are faster, more energy efficient, and much smaller than traditional electronics. And 2D-CRO could be a major part of this technological revolution.
This is all really exciting. But let's remember that we're still in the early stages of understanding 2D-CRO. There's still so much research to do and many challenges to overcome.
You're right. Making 2D-CRO is just the first step. Once we have the material, we need to really study its properties, understand how it behaves in different conditions, and figure out how to use it in different fields.
It's a long road ahead,
Mm-hmm.
but it's a journey that's sure to be full of amazing discoveries and breakthroughs.
Absolutely. And who knows, maybe one day we'll look back on this moment as the beginning of a new era in material science, an era driven by the incredible properties of 2D-CRO and other materials that haven't even been discovered yet.
Well, this has been an awesome deep dive into the world of 2D-CRO. We've covered so much, from its predicted structure and altermagnetic behavior to how it could revolutionize electronics and other technologies.
It's been a really fascinating journey, exploring the frontiers of physics and material science.
But before we wrap up this part of our exploration, I want to touch on something we haven't really talked about explicitly yet.
Uh-huh.
Symmetry. It often gets overlooked, but it's super important in shaping the properties of materials, including 2D-CRO. Are you ready to tackle the mysteries of symmetry?
Absolutely. Symmetry is like the unsung hero of the material world. It's a beautiful and fascinating concept, and it's essential for understanding why 2D-CRO behaves the way it does.
All right, so let's talk about symmetry. To be honest, when I hear symmetry, I think back to high school geometry. And it wasn't exactly the most exciting class.
Yeah, I get that. But symmetry in material science is actually really cool. It's like this hidden code that determines how atoms arrange themselves, and that arrangement in turn determines the material's properties.
No, it's not just about how things look, it's about how they actually work.
Exactly. Think about a building. The symmetry of a building affects its stability. A well-balanced symmetrical structure is stronger. It's the same with materials. The symmetry affects their electronic, magnetic, and even optical properties.
Okay, I see. But what does symmetry have to do with 2D-CRO and this whole altermagnetism thing?
Well, remember how we talked about those oxygen octahedra tilting around the ruthenium atoms?
Yeah.
Well, those tilts actually break some of the symmetry in the material, and that's really important for altermagnetism to happen.
So it's like you have this perfectly symmetrical pattern, and then something disrupts it, and that creates something totally new and unexpected.
Exactly. Think of a perfectly balanced scale, and then you put a tiny weight on one side. It tips the balance and creates a new equilibrium. In 2D-CRO, the tilting of the oxygen atoms is like that tiny weight. It tips the magnetic balance and creates the altermagnetic state.
That's a really good way to explain it. It makes symmetry breaking a lot easier to understand. But there are different types of symmetry, right? We hear terms like inversion symmetry, time reversal symmetry, rotational symmetry. Can you break those down for us?
Sure, let's start with inversion symmetry. Imagine you have a mirror. If the reflection looks exactly the same as the original object, then it has inversion symmetry.
Like folding a piece of paper in half, and the two sides match up perfectly.
Exactly. Now, in 2D-CRO, Those tilted oxygen octahedra break the inversion symmetry. If you were to flip the material, it wouldn't look exactly the same. And this broken inversion symmetry is key for altermagnetism.
So in this case, breaking the symmetry is a good thing. It's what makes 2D CRO special.
Yeah, exactly. It opens up all these possibilities that wouldn't be there in a perfectly symmetrical system. Now, time reversal symmetry is a little more abstract. It basically means that if you reverse time, the laws of physics would still be the same.
So if you could rewind the universe,
Yeah.
everything would happen in reverse.
Yeah,
But the rules of physics wouldn't change.
right. But in some systems, like 2D CRO, time reversal symmetry can be broken. And when that happens, you get some really interesting phenomena, like the quantum anomalous Hall effect we talked about.
So breaking time reversal symmetry is what allows for those special edge states where electrons can flow without resistance.
Exactly. It's a mind-blowing idea. But it's a fundamental principle behind some of the most advanced materials science research today.
Okay, 2 down, 1 to go. What about rotational symmetry?
Rotational symmetry is all about how something looks when you rotate it. Imagine a square. If you rotate it 90 degrees, it still looks like a square. That's rotational symmetry.
So you spin a square like a record. It looks the same at 4 different points during each rotation.
Exactly. And 2D CRO has rotational symmetry too. The way its atoms are arranged gives it fourfold rotational symmetry.
So you could spin a sheet of 2D CRO by 90 degrees, and it would look the same.
Right. And this rotational symmetry, together with the broken inversion and time reversal symmetries, all contribute to the unique electronic and magnetic properties of 2D CRO. It's like they all work together to create this amazing material.
Yeah, this has been a really cool deep dive into symmetry. I never thought I'd be so interested in symmetry.
It's one of those things that seems simple at first, but the more you learn about it, the more complex and interesting it gets.
It's like this hidden language
Yeah,
that governs everything in the universe, from galaxies to atoms.
I like that. And with 2D CRO, it's this interplay of symmetries that gives it the potential to change technology as we know it.
This deep dive has been incredible. We started by exploring this new material called 2D CRO. We talked about altermagnetism, learned about buried curvature and topological states,
Yeah.
and even uncovered the mysteries of symmetry.
It's been a whirlwind tour of some really cool physics and material science. I hope you've enjoyed it as much as we have.
Absolutely. This is the kind of stuff that reminds you how much we still don't know and how many amazing discoveries are still out there waiting to be made.
That's what makes science so exciting. It's all about exploring, discovering, and pushing the boundaries of what we thought was possible.
Well said. And to all our listeners out there, keep exploring, keep asking questions, and keep your minds open to the wonders of science. Who knows, maybe you'll be the one to make the next big breakthrough.
Until next time, keep those imaginations going.